Hello, welcome to this channel Chemistry Made Easy by Dr. ARM. Today we will see the next part of this atomic structure, that is the Schrodinger's wave equation. This Schrodinger's wave equation is given in 1926. And this is used to describe the wave properties of an electron in terms of position of the electron, then mass of the electron, total energy of the electron, and the potential energy of the electron. So these terms are used to describe the wave properties of an electron present in the atom. In the last lecture we have seen that according to Bohr's theory, the circular orbits were proposed, but these orbits were not accepted everywhere in multi-electron systems, because the orbits were considered to be elliptical in nature, and each orbit is characterized by its specific wave function, and this wave function is specifically used to obtain the energy, that is total energy and potential energy, as well as position of electron in orbitals and not in orbits. So the energy of orbits is difficult to consider, but it is convenient to consider, or it is helpful or useful to consider the characteristics of electron as a wave in case of orbitals. So here we will discuss that the orbital is having wave function of orbital is psi. Psi is used psi is the designation to describe wave function of an orbital. So this wave function describes atomic orbital, and in its simple form of the Schrodinger's wave equation, we are describing this wave equation as H psi equal to E psi. Here the H is Hamiltonian operator, and here E is the energy of an electron, and specifically of the orbital in which it is located. So this is the short form, we say, of the Schrodinger's wave equation. Here H is the Hamiltonian operator, E is the energy of an electron, and psi is the wave function of an electron, or we can say the orbital. Then when we are considering a mono-electron system like hydrogen, then this Schrodinger's wave equation is exactly fitting to this hydrogen atom to describe the single electron. Means whenever the system or atom has only one electron in the orbits or orbitals, then this Schrodinger's wave equation is exactly fitting or exactly suitable to provide the calculations. But there are multi-electron systems in which there are various number of electrons, and each electron is characterized by its specific orbital or specific value of psi and specific energy, specific value of psi and specific energy. So the psi value and energy value of that particular electron, means that particular orbital, is called a quantization of that orbital. So this is called a quantization of an electron. So describing the value of psi and value of E, we are quantizing the electronic orbitals. So in this way, every electron has different value of psi and different value of E. So every electron is characterized by these two values, that is psi value and energy value. Therefore, the Hamiltonian operator can be calculated or used to calculate energy of energy levels. So, Hamiltonian operator used for calculating energy levels, and here it is means the H value, that is Hamiltonian operator H, is given by minus h square upon 8 pi square m, minus h square upon 8 pi square m into delta square upon delta x square plus delta square upon delta y square plus delta square upon delta z square minus z into e raised to 4 e raised to 2 z into e square upon 4 pi epsilon 0 into square root of x square plus y square plus z square. So this gives the value of h, that is Hamiltonian operator, and here this value gives us two parts of information. So we can get the two types of information. So this particular part gives us the kinetic energy of an electron, whereas this portion gives us potential energy of an electron, and we can see here potential energy of an electron. Here this portion, that is minus z into e square upon 4 pi psi 0 epsilon 0 into square root of x square plus y square plus z square. This gives us the potential energy, means the result of potential energy means the result of the electrostatic attraction between electron and the nucleus. So potential energy of an electron is the result of electrostatic attraction between electron and the nucleus. Nucleus is positively charged species. Electron is negatively charged species. So nuclear force of attraction exerts electrostatic force of attraction on the electron. So nearer the electron to the nucleus, the electrostatic force of attraction exerted by the nucleus will be stronger. Means the strength of this nuclear force of attraction means this potential energy depends upon the distance between the electron and the nucleus. So shorter the distance between the nucleus and electron, the larger will be the value of this potential energy. So this value goes on decreasing with the increasing distance between the electron and the nucleus. So as we move away from the nucleus, so for example, if we consider this nucleus, this is the nucleus. So if this is n is equal to 1, so as we move here away from the nucleus and say this is the infinity, so this is the infinity energy level, and this is 1, 2, 3, 4, etc. So this is the shorter distance. So this distance is shorter. So electron present here will have stronger electrostatic force of attraction, and therefore it is strongly bound to this nucleus. So the potential energy associated with this electron will be larger. And as we move away from this nucleus like this, the potential energy will go on decreasing. In case of this infinity value or energy level, the potential energy will be 0. So this term is called also, this term is also called V, that is potential energy. Now this kinetic energy, here if we see the various terms, here H is Planck's constant, M is the mass of the electron, and this x, y, z are the coordinates. So we are assuming that the electron is moving in the x direction, and depending upon this we can get the various values of psi. So here this distance, that is, here we can see the square root of x square plus y square plus z square gives us the value called r, that is the distance between the nucleus and electron under consideration, or for which we are calculating the potential energy, kinetic energy, and we are finding out the mass and position. It means that this information is associated with the orbital, that is associated with the specific electron. It means we can say that particular electron is present, or it has very high probability, means that orbital shows that the electron density, where the probability of finding an electron is more. Here another term is there, that is this psi 0. This psi 0 is the permittivity in vacuum. Psi 0 indicates the permittivity in vacuum. Now when we are using this Hamiltonian operator, when this operator is used in the equation in order to obtain the psi. So after applying this Hamiltonian operator to the wave function, that is psi, we get the equation as square root, we are using here square bracket, this h square minus h square upon 8 pi square m minus h square into 8 pi square m into delta square upon delta x square plus delta square upon delta y square plus delta square upon delta z square. So this is the one part of this equation, plus we are using this V as we have shown in the earlier equation, that is potential energy of the electron or that particular orbit or orbital. So here this V indicates the potential energy, which is also explained by this, considered using this x, y and z coordinates. Then this is further described by this wave function psi in x, y and z coordinates. So here the energy of this particular electron is given by E into, means in the first equation we have seen that the Hamiltonian operator H psi is equal to E psi. So here we will get E psi and x, y, z, that is the coordinates which describe the exact location of the electron, that is z. So here the value of V is, we have seen, that is the minus z into e raised e square. Here the value of this V is minus z into e square upon 4 pi square upon 4 pi epsilon 0 into, if we replace this value, then R we have seen in the last equation, that is the square root of x square plus y square plus z square is taken as R. So into R. So here the equation can be written using these various terms. So on this basis of various energy terms used, we say that the potential energy is the result of electrostatic attraction between the nucleus and electron under consideration. So we can have different potential energies depending upon the specific electron we are considering in the given atom. So attractive forces like these between positive nucleus and negatively charged electron are defined conventionally. Then we have also seen that the distance, that is the value of R, when it is smaller, then the potential energy for the electron is larger. As the R value, that is distance between the nucleus and electron, goes on increasing, the value of potential energy also goes on decreasing. It means when we consider the maximum or infinite distance from the nucleus, the value of energy will be 0. As in when we consider the psi value, so this psi value matches the orbital under consideration, atomic orbital under consideration, and there is no limit to the number of solutions. Means we can have a various electrons, number of electrons in the atom, and for every electron we can have the different values of psi values and the various values such as the potential energy and kinetic energy values. So we should understand that for every electron, the characteristics of that electron, that is potential energy and kinetic energy and the wave function, is separate or distinct or specific. It is not everywhere the same. Means the value of psi and the value of energies are not everywhere the same for every electron. It varies for every electron present in the atom. So the psi describes the wave properties for a given electron in a particular orbital. So the probability of finding an electron in an atom is described in terms of atomic orbitals. So every atomic orbital has the specific value of this psi value as well as energy value. Then we should understand that when we consider, say, this is a particular orbital, then there is electron density, means the electron, this we can say so this dots or the region we have specified here. So this region shows the probability of finding an electron. So we can consider, or we can say that in this particular region in the space around the nucleus, the probability of finding an electron is maximum, and this region is called orbital. And this orbital may have different size and shape. So depending upon the nature of electron density, the nature of orbital is also different. So this electron density is given by psi square. So psi square describes the electron density of the atomic orbitals. A number of conditions are required for a physically realistic solution of psi. So what are these conditions? The first condition is that the wave function psi must be single valued. Means for every electron there should be a single value of wave function. One electron cannot have more than one, means different values of psi. There should be only one value of the psi. There cannot be two probabilities, means there cannot be two probabilities of an electron to have different position in the space. Then second condition is that the psi and its first derivative must be continuous. The probability must be defined at all positions in space and cannot change abruptly from one point to another. Means when we consider a single electron, we have to understand that it has only one at any instant. It is present at only one point, and we cannot consider its existence at more than two or more than one different positions. The psi must approach zero with the increasing value of r. That we have already discussed. Means with the larger the value of r, the smaller the value of psi. Then the integral value, that is for all space. Then this integration for psi a into psi b into this delta tau is equal to, first there is one condition, this is 1. When it is 1, then it is said that the total probability of an electron being somewhere in space is called the normalizing the wave function. So this shows that the normalizing of the wave function. It means the total probability of an electron being somewhere in the space is 1. It cannot have different values. When another value, when this psi a into psi b into d tau is equal to 0, that is, it shows that all orbitals in an atom must be orthogonal, or orbitals in an atom must be orthogonal. In some cases, the orbitals are perpendicular to each other. We can take the example of px, py and p3. So all these orbitals, this orbital is lying in the direction of x-axis. This is lying in the direction of y-axis, and this is lying in the direction of z-axis. So these all orbitals are perpendicular to each other. So with this we will stop our discussion and we will go for another point in the next lecture. Till then, goodbye. See you next time. Please keep subscribing to this channel and share your views with us in your comment box. Please also share this channel or this link of this channel to your friends. Subscribe, ask your friends to subscribe this channel, and please press bell icon button and like button so that we can consider, or your comments will suggest us various things and we can improve our contents. So thank you very much for watching this